Welcome to this episode of Real Chemistry. In this video, we're going to be talking about isochoric heating of an ideal gas. Isochoric is kind of a strange word, but what that means is constant volume. So it means constant volume. Basically, we're here looking at heating up a gas where it's in a sealed container that doesn't change in volume. So let's go ahead and take a look at that process. A problem you might solve under isochoric conditions would look like this. 1.2 moles of an ideal gas is warmed from 177 Kelvin to 255 Kelvin at a volume of 7 liters. Find delta U, delta H, W, and Q. So remember, isochoric means no changes in volume. So the basic circumstance we're looking at here is imagine we have a sealed container. Inside of it we have our ideal gas. And then down below it you have a flame. A very big burning flame with a little blue down there. Beautiful. Okay, so all we're doing is warming it up. You can see that we go from 177 Kelvin to 255 Kelvin. So we're adding heat to our system. So this should make it clear that our Q then is going to be positive because we're increasing the internal energy of our system by adding heat. If you're still having trouble identifying the signs of Q and W, I recommend you check out the video I'm going to link to below on Q and W and if they are positive or negative. So let's go ahead and calculate then these four variables. The easiest one to do is actually work. Remember that this volume here doesn't change. It's a fixed container of a fixed size. And we know that work is equal to negative P delta V. Since our volume is not changing, that means our work is zero. If little dV here is zero, when I multiply P times zero, I'm going to get zero. And so that's what we get. Work is zero. So that's our first variable. Pretty straightforward. Next, let's go ahead and solve for Q. Q we get from a heat capacity process. So remember here we're just warming up a sample of gas and we're doing it at constant volume. That means our heat capacity we're interested in is constant volume. So I'm going to put a little V there on both sides of our equation. If we rearrange that, we'll get dt times CV equals dQ. Now, if I integrate that and assume that heat capacity is not a function of temperature, which is true in this case, then we'll get delta T times CV equals Q. Lastly, I need to keep in mind that when I look at CV down here, that this is actually a molar heat capacity. So I could draw it as CV/M. And that's because it depends on the gas constant, which has a units of joules per mole. So if I want to get just joules, then I have to actually add a unit of moles there. When I did delta T times CV, I would get the heat that was transferred for just 1 mole. So if I'm doing anything other than 1 mole, I got to multiply by that. Okay, let's calculate Q then. Moles is 1.2 times change in temperature, which is 255. That's my final temperature, times my initial temperature of 177, times my gas constant times 3/2 for my molar heat capacity. And my gas constant is 8.3145 joules per mole Kelvin. So remember that whenever we use a gas constant in these calculations, we want to use the one in terms of joules, which is the 8.3145 version. Okay, that's going to give me Q. In this case, Q is going to be equal to 1200 joules once I round it there for 2 sig figs, because the fewest number of sig figs in that multiplication process is 2. All right, so that's Q and W. Now that we have Q and W, we can use our first law of thermodynamics over here to get our change in internal energy. So delta U is equal to Q plus W. So delta U is equal to 1200 joules because our work is zero. So delta U and Q for an isochoric process are actually exactly the same. Okay, lastly, let's calculate enthalpy. Delta H is equal to delta U plus delta PV. So I'm grabbing my enthalpy equation right here. And in this case, we want to pay special attention to the delta PV. Notice I don't really have any information directly about the pressure or volume. And that makes it easiest to go ahead and use the ideal gas law and substitute PV for nRT. Notice the ideal gas law is telling me multiplying pressure times volume is the same as multiplying N times R times T. So let's erase that and instead put delta nRT. So that delta nRT is considering the possibility that all of those variables in there could change. But remember, the number of moles is constant because we have a sealed container. And the gas constant is, of course, constant. So the only thing changing there is temperature. So we get delta H equals delta U plus nR delta T. Temperature is the only thing that changes. So delta U, we plug in 1200 joules plus N, which is 1.2, times the gas constant, 8.3145, times my change in temperature, which is still 255 minus 177. Now, one thing you want to be careful about is you want to grab for delta U the original number that came out of your equation over here. So I've rounded for sig figs, but when you use that number in a subsequent calculation, you don't want to use the rounded number because that leads to round off error. So I'm going to go ahead and plug this all in my calculator first, and then I'm going to add 1.2 times 8.3145 times the change in temperature to that. When you do that and round for 2 sig figs, you get 1900 joules for enthalpy. So that's my enthalpy, 1900 joules. Notice that my Q is positive because I am adding energy to my system. My delta U is positive, I'm adding energy to my system. And my enthalpy turns out to be positive too. So thanks for watching this episode of Real Chemistry. Here you can see a quick summary of all the different equations that we've used as we've calculated Q, W, delta H, and U for these different processes with ideal gases.